everyone, welcome back. This is part 6 for our chemical bonding series in grade 11 chemistry. Okay, so today we're going to focus on polarity in covalent molecules. Let's begin with answering this question: what is polarity, or how do we define polarity? Okay, so polarity in simple terms, it's defined as an even sharing of electrons or an even distribution of electrons. So polarity is an even distribution of electrons. Okay, this uneven distribution of electrons is defined as polarity. So where does this uneven distribution comes from? Some elements or some atoms tend to pull the shared pair of electrons more than other elements. This is known as electronegativity. Electronegativity. Okay, so electronegativity is ability of atoms to attract shared pair of electrons. So the more the pull or the more the difference in electronegativity will result in a higher or in a more polar molecule. Now let's look at an example. Our first example will be HCl or hydrochloric acid. So in HCl, chlorine is more electronegative than hydrogen. What does this mean? Chlorine will tend to attract this pair of electrons more towards itself, making chlorine partially negative charge and hydrogen partially positive charge, okay? Because electrons are being taken away from hydrogen, it will tend to have partially positive charge, and as chlorine is attracting or taking the electrons, it will tend to have a partial negative charge. And then to represent the dipole moments, or the flow of the electrons, we use an arrow, okay? An arrow pointing towards the more electronegative atom. So in this case, hydrochloric acid is a polar molecule, or HCl is a polar molecule. This is due to the fact that chlorine pulls or attracts this shared pair of electrons more towards itself than hydrogen. Now let's talk about polar and non-polar substances. Okay, let's compare polar and non-polar compounds. So just because a molecule has some polar bonds does not mean the molecule itself is polar. This is due to the fact that molecular polarity depends on two factors: bond polarity and shape. Okay, molecular polarity. Molecular polarity depends on two factors. The first one is bond polarity, and the second one is shape. Okay, so now to describe or to classify a given molecule as polar and non-polar, we have to consider two factors. The first one being the bond polarity, and the second one being the shape. Okay, the shape defines if the molecule is symmetrical or asymmetrical. We'll see some examples. Let's consider two molecules. Okay, the first one will be carbon dioxide, and the second one will be water, H2O. Let's begin by drawing their Lewis structures. So for carbon, as you can recall from our previous videos, we're going to have two double bonds, okay? This is carbon dioxide. And then when it comes to water, we're going to have oxygen in the center with two hydrogens. Now, to compare the polarity of carbon dioxide and water, let's draw the dipole moment, okay? For carbon dioxide, oxygen is more electronegative than carbon, so this is the direction of the dipole moment, and this will also be the direction of the dipole moment. So as you can see, here we have a symmetrical molecule. These two dipole moments, you can consider this as two vectors, okay? As two vectors. For example, the first vector going 2 Newton or 20 Newton going to this direction, and again 20 Newton going to this direction. So the nets or resultants of these two vectors would be 0. This works. This concept also works for polarity. Okay. Now let's look at these two dipole moments. So as you can see, these two dipole moments are pointing in opposite directions. Okay. This makes them cancel each other out. So carbon dioxide is now symmetrical. Symmetrical, okay? These two bonds or these two dipole moments are symmetrical as the shape is linear. Okay? So this is a symmetrical molecule, so its polarity will be non-polar. Okay? Carbon dioxide is non-polar. This is due to the fact that this is symmetrical. The shape is symmetrical. Okay, now let's look at water molecule. So obviously oxygen is more electronegative than hydrogen. So we're going to draw our dipole moments in this way. Now let's add these two vectors or these two dipole moments. As you can see, they are not canceling one another. So instead, they are going to be added to make a net dipole moment. Okay? So this shape or these two bonds in water are not symmetrical. They are asymmetrical. Okay? They're what? Asymmetrical. They are asymmetrical due to the fact that these two bonds are asymmetrical. The two dipole moments here will be added to give a net dipole moment, resulting in a polar molecule. Let me ask you one question. Why do you think this bond is straight, linear? The molecular shape here is linear, and then the molecular shape here is bent. These two bonds, the two hydrogen bonds, are not straight like this, but instead they are bent. Why do you think is the reason here? This is due to the fact that the lone pairs of electrons in oxygen, push these bonding pairs, and then defines the shape of water as bends, okay? Not linear, but bends, okay? Now let's look at some more examples, okay? Let's compare two molecules here. This one is trichloromethane, CHCl3, and then this one is tetrachloromethane, CCl4, okay? This trichloromethane is also called chloroform. Now let's compare the the molecular polarity of these two molecules. Let's begin by drawing their Lewis structure. So let's begin with this one now. Now let's draw the dipole moments together. So obviously from hydrogen and carbon is more electronegative. So the dipole moment will be in this direction, okay? And then from carbon and chlorine, it's chlorine that is more electronegative. So we're going to draw our arrows downwards like this. Okay? Now, what we can say from this is these four bonds are not symmetrical. They are asymmetrical. This is due to the fact that, as you can see, the dipole moment overall is going down. Okay? So we can represent it by this symbol here. So this is CH bond, and then this is CCl bond, this is CCl bond, this is CCl bond. So this is not symmetrical, as this is different bond from these two. From these three. So this is asymmetrical. This is asymmetrical, okay? And then let's come to the tetrachloromethane. So here we're going to have a carbon in the center and 4 chlorines surrounding it. So then the dipole moment for this bond will be like this. Like this. So as you can see here, 4 of these bonds are, originating from the center and spreading out into 4 directions equally, meaning this is symmetrical molecule. So as you can see, these 4 chlorines are arranged tetrahedrally around this carbon, meaning spacing one from another in a 109 and 5 degrees. Okay, so these 3-dimensional arrangements of these 4 chlorines around carbon makes them symmetrical. So this is symmetrical. This arrangement is called symmetrical. So if the arrangement or if the shape is symmetrical, the molecule will be non-polar. The molecule will be non-polar as these dipole moments can cancel one another, okay? But if it is asymmetrical like this, if it is not symmetrical, the molecule will be polar as the dipole moments will add with one another, not cancel out, okay? Now let's look at some complex molecules. Let's try to analyze their molecular polarity, okay? So let's begin from SF6, sulfur hexafluoride. So in sulfur hexafluoride, we have sulfur in the middle and 6 fluorine surrounding it. So as you can clearly see, and then as you can clearly recall that fluorine is the most electronegative element. So the bonds, six of these SF bonds, they are all polar bonds. But despite the fact that 6 of these bonds are polar, overall this SF6 is non-polar. And then the reason for this is due to the fact that this is symmetrical, because these 6 fluorine atoms are arranged in octahedral structure. Okay, so this is non-polar. This is non-polar. Now let's talk about PCl3, phosphorus trichloride. Okay, in PCl3, we're going to have P in the center. We're going to have P in the center and 3 chlorines with a single or with a lone pair around phosphorus. So as you can see, is obviously these PCl bonds are polar, as chlorine is more electronegative than phosphorus again. But the shape or the arrangement of these 3 chlorine atoms, or the arrangement of these 3 PCl bonds, is not symmetrical. This is due to the fact that this lone pair of electrons in phosphorus pushing this bonding pairs of electrons away, making them not spacing out as much as possible. So the resulting shape or structure will be asymmetrical, okay? So due to the fact that this is asymmetrical, and then overall the PCl3 will be polar molecule, okay? Will be polar molecule. In our third example, we're going to compare ammonia, NH3, and NF3. Let's compare the polarity of these 2 bonds, okay? Let's start with drawing their loose structures. So as you can see, 2 of these molecules have a lone pair of electron around the central atom, and then 3 bonding pairs. So the shape is going to be trigonal pyramidal. But regardless of they have the same shape and stuff, they are both polar molecules, both polar, and then this is due to the fact that this is asymmetrical from the presence of this lone pair of electrons. But let's compare which one is more polar. Pause the video and try to predict which one is more polar of these 2 molecules. Okay, hopefully you have answered it as ammonia. Ammonia is more polar than NF3. Why do you think is ammonia more polar than NF3? As you can see, here we have nitrogen bonded with hydrogen and fluorine bonded with nitrogen. So the electronegativity difference between hydrogen and nitrogen is much more bigger than electronegativity difference between fluorine and nitrogen. So ammonia is more polar. And this is due to the fact that the electronegativity difference between hydrogen and nitrogen is greater than that of electronegativity difference between fluorine and nitrogen. Why does polarity matter? Why do we need to study it? Where can we apply the knowledge of polarity? So polarity affects physical and chemical properties of molecules, okay? For polarity affects solubility, boiling point, and reactivity. Let's look at them one by one. Let's begin from solubility. Do you remember or do you recall this? Like dissolves like. Like dissolves like. What does this mean? Polar substances will only be dissolved in polar solvents, okay? Non-polar substances will only be dissolved in non-polar solvents. So polar dissolves polar, non-polar dissolves non-polar. So understanding the polarity of a molecule help us predict its solubility in polar solvents like water and other solvents, okay? And then let's look at boiling points. Boiling points is also affected by polarity. So when we talk about boiling points, we're going to focus on the intermolecular forces holding the molecules together. Okay. So depending on the polarity of the given molecule, a molecule can have different intermolecular forces, the ones that are strong and the ones that are weak. Okay, so the more polar the molecule, the more strong intermolecular force will it have. If a molecule has strong intermolecular force holding its particles, and then it will require higher energy to be overcome. Okay, meaning it will have higher boiling point. So polarity obviously affects boiling points. The third one is reactivity. So some polar molecules are very reactive due to the fact that they are available or easy to be attacked by an electrophile, nucleophile, cation, or anion. Okay, so the more polar the molecule, the more reactive it is. So this is it for today. Let's look at our key takeaways. Okay, the first one is molecular polarity depends on two factors: bond polarity and shape. Okay, just because a molecule has polar bonds does not mean the entire molecule is polar compound or polar molecule. Okay, because it also depends on the shape or the asymmetry or symmetry of the molecule. The second key takeaway is understanding polarity. Helps us predict physical and chemical properties of the given molecule, like melting and boiling point, solubility, and reactivity. There you have it. This is it for polarity in covalent compounds. Next time, we're going to look at intermolecular forces. But if you have questions from today's discussion or any other chemistry topic that you're studying, feel free to comment and do a video on it, okay? Thank you. See you next time.